When we stopped last time, we were studying heat transfer during film condensation on a vertical plate. I was deriving an expression for the heat transfer coefficient and following the derivation, which was first done by Nusselt long ago in 1916. And if you recall, where we stopped, after making a certain number of simplifying assumptions, we had applied the Newton's second law of motion, that is one of our basic fundamental laws, and derived an expression for the velocity profile in the liquid film. Then we had derived an expression for the mass flow rate in the film, the liquid mass flow rate in the film, and then taken the differential of that to show that if you go from a section Z down to a section Z plus dz, then the mass flow rate increases by the differential amount, and we had an expression for that, and that is where we stopped. So, let me just put down those expressions again to recollect. We were studying heat transfer during film condensation on a vertical plate. And our objective is to derive an expression for H, the local heat transfer coefficient, and H bar, the average heat transfer coefficient during the condensation process. When we stopped last time, we had come about halfway through the derivation. We had derived an expression for the velocity profile based on applying Newton's second law of motion. We had got the velocity profile in the downward direction. The velocity is V z given by rho g by mu y delta minus y squared by 2. That was the first thing we had derived. Then we had calculated the mass flow rate with the help of this velocity profile, the mass flow rate through the liquid film, and for that we had an expression m dot is equal to rho squared g, b is the width of the plate in a direction at right angles to the paper, divided by 3 mu delta cubed, and taking the differential of that, we had got the expression d m dot by b. M dot by b is the mass flow rate per unit width of the plate, is equal to rho squared g by mu delta squared d delta. This is where we had stopped last time. And what this really implies is, when you get a differential amount, what it implies is that if you are moving down the plate, let us say, let me draw the sketch of the plate again. If you are moving down the plate, this is the top of the plate, this is the z direction downwards, and this is the liquid film. Then if you have a cross section z, and if you have a cross section z plus dz, this is at z and this is at z plus dz, then from this cross section at z to this cross section at z plus dz, the mass flow rate per unit width increases by an amount rho squared g by mu delta squared d delta. And where does that increase come from? That increase comes from the fact that we have condensation taking place. So, out here at the cross section z, the mass flow rate is m dot by b. Out here at a section which is z plus dz, you move the distance dz forward, it is m dot by b plus d of m dot by b, and obviously the difference between the two has been made up by condensation which is taking place from z to Z plus dZ at the liquid vapor interface. That is how the difference is being made up. So, this quantity here which is coming in is d of m dot by b, and for this quantity we have the expression d m dot by b is equal to rho squared g by mu delta squared d delta. So, if conservation of mass is to be satisfied, if the equation of continuity is to be satisfied, it follows that this is the mass balance, mass flowing in, mass flowing out. The difference is made up by the condensation which is taking place from Z to Z plus dZ. This is how continuity is satisfied. Now, what remains is to apply the remaining fundamental law, which is the first law of thermodynamics. So, that is what we will be doing next. We will now apply the first law, because we have used Newton's second law, we have satisfied continuity. So, now we go on and decide that we will apply the first law of thermodynamics. So, let us do that now. We say, let us take a control volume which is a slice, and let me show that slice just for the, let us take as our control volume for applying the first law. Let us take this slice Z and Z plus dZ, a slice of the film between the section Z and Z plus dZ, and let us apply the first law of thermodynamics to this slice. Now, an enlarged view of this slice is shown here. This is an enlarged view of the slice, and out here you have the, first of all you have the mass balance m dot by b, which I had shown a moment ago. Then d m dot by b is the mass flowing in by condensation, that is vapor being converted into liquid, and this is m dot plus d m dot by b, which is the mass flowing out, that I had just shown a moment ago in another sketch. Now, if I want to apply the first law to this mass balance, to these masses flowing in and out, I must multiply them by the enthalpy per unit mass. So, let us do that. So, out here now where we have m dot by b flowing in, you multiply by the enthalpy per unit mass H f. H f is the enthalpy of saturated liquid. So, out here I am multiplying by that. Remember, we have made an assumption that we are going to neglect subcooling. So, we will just multiply this by H f, which is the enthalpy per unit mass of saturated liquid. In the flow going out, again it is saturated liquid. So, again I multiply the mass flow rate by H f, and in the flow coming in, that is, this is the condensation taking place here, I multiply by H f plus lambda, because out here it is this enthalpy of saturated vapor which I have to take. The saturated vapor condenses at the liquid vapor interface and then enters this control volume. So, it brings with it enthalpy per unit mass H f plus lambda, lambda being the latent heat of vaporization. So, this is our enthalpy balance. This is the enthalpy flowing out, this is the enthalpy flowing in at the section Z, this is the enthalpy flowing in at the liquid vapor interface, because vapor is condensing at the interface. All right. Now, with this as a background, let us apply the first law of thermodynamics to this. So, we say consider the control volume delta dz, the slice delta dz, neglect subcooling, consider the control volume and apply the first law of thermodynamics. Neglect subcooling, as I have said, that is one of our assumptions. Neglecting subcooling, then rate at which enthalpy, now I am applying the first law, rate at which enthalpy leaves control volume minus rate at which enthalpy enters the control volume is equal to rate of heat transfer, rate at which heat flows by heat transfer to the control volume. That is the first law statement. Now, what is the left hand side? The left hand side in this case will be the left hand side in this case will be the left hand side in this case will be m dot plus d m dot by B multiplied by H f. This is the enthalpy leaving the control volume minus the enthalpy entering at the cross section Z, that is m dot by B into H f, minus the enthalpy entering where the vapor condenses and becomes liquid, multiplied by, this is the rate at which it enters and this is the enthalpy per unit mass, because this is saturated vapor being converted into saturated liquid. So, multiply by H f plus lambda. So, the left hand side is nothing but, on simplification, it is minus d of m dot by B lambda. Now, the right hand side of the expression into which we want to substitute. The right hand side is the rate of heat transfer to the control volume. This is, let me just draw the control volume here. This is our control volume like this. This is the liquid film here and this is the wall, all right, and this is our control volume. Now, the heat transfer to the control volume takes place through this phase where the liquid comes in contact with the wall. This is the wall. The liquid is flowing down like this, this is the wall here. So, this is where the heat transfer to the control volume takes place, and since it is a fluid flowing across a wall, we know from our study of convection that the rate of heat transfer will be minus k, Fourier's law will apply at the wall, minus k dt dy at y is equal to 0 multiplied by the area dz, and we are taking a unit width. So, into 1. So, this is the rate of heat transfer to the control volume, and that is, we have made an assumption that we are going to take the temperature profile to be linear. So, it is nothing but minus k. Now, dt dy at y is equal to 0 is nothing but T s minus T w, since we have a linear temperature profile in the liquid, divided by delta multiplied by dz. So, we have the left hand side an expression here, the right hand side an expression here. Now, let us equate the two and we get minus k T s minus T w divided by delta, the whole thing multiplied by dz is equal to d minus d m dot by B lambda which in turn is equal to, we have an expression for m dot by B, d m dot by B. So, we get minus lambda rho squared g delta squared divided by mu d delta. That is our expression which we get by substituting into the first law of thermodynamics. The left hand side is the rate of heat transfer to the control volume. The right hand side here is the right hand side, I put it the other way now, the right hand side I put on the left hand side. So, the right hand side is the rate of heat transfer to the control volume, the left hand side is the rate at which enthalpy flows out minus the rate at which enthalpy flows into the control volume. Let us clean up that expression a little. If you clean up the expression a little, we get delta cubed d delta. Delta cube d delta is equal to k T s minus T w multiplied by mu divided by lambda rho squared g, the whole thing multiplied by d z. This is what we get on substituting on applying the first law of thermodynamics to that slice, which is delta multiplied by d z. Now, let us integrate this expression. If I integrate this expression, I will get delta to the power of 4 divided by 4 is equal to k T s minus T w mu divided by lambda rho squared g multiplied by z plus a constant of integration. Now, in this case, we know that right at the top of the plate, where the condensation begins, that is at z is equal to 0, delta must be equal to 0. Theoretically, at least, that is a condition we can apply. So, if you put that in, then this constant, which I will call as C 1, therefore, C 1 is equal to 0. So, on integration we get delta to the power of 4 divided by 4 is equal to, the constant being 0, k T s minus T w divided by mu divided by lambda rho squared g multiplied by z. Or if I want an expression for the film thickness, I will get, if I want an expression for the film thickness, I will get delta is equal to 4 k T s minus T w mu z divided by lambda rho squared g divided by lambda rho squared g, delta is equal to all this to the power of 1/4. That is the expression we get for the film thickness after applying the first law of thermodynamics. Now, let us now use this to calculate the local heat transfer coefficient. First of all, let me define. We want an expression now for the local heat transfer coefficient. We want an expression for the local heat transfer coefficient. We will define it as follows. We will say H is equal to, as always, we are being consistent, the local heat transfer coefficient is equal to the heat flux at the wall divided by the temperature difference T s minus T w. This is how we will define a local heat transfer coefficient, that is the local heat flux at a cross section Z divided by the temperature difference T s minus T w. Now, in this case, the heat flux at the wall, we know can be readily put down in terms of the temperature difference, because it is a linear temperature profile. So, we can say this is equal to heat flux at the wall is nothing but K T s minus T w divided by delta. That is the heat flux at the wall, because we have a linear temperature profile, and that is to be divided by T s minus T w. So, this simplifies to nothing but the expression for H simplifies to nothing but K divided by delta. Now, we have derived already an expression for the thickness, film thickness delta. So, we get H is equal to, therefore, H is equal to lambda rho squared g K cubed divided by divided by 4 T s minus T w mu z. This is the whole thing to the power of 1 by 4. The whole expression to the power of 1 upon 4. So, this is our expression, our expression for the local heat transfer coefficient, and this is an important expression. We put an arrow on it to indicate that this is what we were looking for, one of the things we were looking for, an expression for the local heat transfer coefficient. Now, what is its characteristic? Look at it. Lambda, rho, g, k, T s minus T w and mu are all constants. So, effectively what I am saying is that from this looking at it, what you are saying is H is proportional to Z, the distance along the plate counted from the top downwards, to the power of minus 1 upon 4. So, that is the type of variation of the local heat transfer coefficient we are getting. Or if I were to plot this, let us say if I had a graph, just sketch it, and if I were to plot H against Z, that is moving downwards along the plate, then the variation of H is going to be something like this, because it is Z to the minus 1/4. That is the kind of variation we are going to get for H. Now, let us get an expression for the average heat transfer coefficient. The average heat transfer coefficient H bar, average heat transfer coefficient H bar would be given by, quite logically would be given by H bar is equal to 1 upon L integral 0 to L H into d z. The H bar is the average value of H over a length L of the plate. So, I want a plate length, I want an average value of H bar over a length L of the plate. All I do is integrate H over that length L and take 1 upon L of that. That gives me the average value of the heat transfer coefficient. So, let us calculate an expression for H bar now. The average, for the average heat transfer coefficient, if I put in, I can my expression for H, I will get H bar is equal to 1 upon L, the integral 0 to L lambda rho squared g k cubed divided by 4 T s minus T w mu z, the whole thing to the power of 1 upon 4. This is my expression for H into d z. and on performing the integration, which is very simple, I will simply get this is equal to 4 upon 3 lambda rho squared g k cubed divided by T s minus T w mu L. Four upon 3 multiplied by, I missed a term here, multiplied by 1 upon 4 to the 1/4, multiplied by 1 upon 4 to the 1/4 into lambda rho squared g k cubed upon T s minus T w mu L, the whole thing to the power of 1/4, or it gives on simplification you get 0.943 into square bracket lambda rho squared g k cubed divided by T s minus T w mu L, the whole thing to the power of 1/4. So, this is our expression for h bar, and this is the next important expression which we wanted to derive. We wanted to derive an expression for h and we wanted to derive an expression for h bar. So, h bar is 0.943 lambda rho squared g k cubed upon T s minus T w mu L, the whole thing to the power of 1/4. Now, h, the local heat transfer coefficient at the bottom of the plate, if I ask you if it is a plate of length L, h at z equal to L is nothing but lambda rho squared g k cubed divided by 4 T s minus T w mu L, the whole thing to the power of 1/4. That is our value of the local heat transfer coefficient at the bottom of the plate at z equal to L, if I take a plate of length L. So, it follows that the average heat transfer coefficient, h bar is related to the local heat transfer coefficient at z equal to L. I repeat, the average heat transfer coefficient for a plate of length L is related to the local heat transfer coefficient at z equal to L by the expression h bar for a length L is equal to 4 upon 3 into h at z is equal to L. That is the relationship between the average and the local heat transfer coefficient. Or again, if I were to plot a graph, suppose to show h against z, if I am plotting h against z, and let us say this is z equal to L, this point is z is equal to L, and let us say the variation of h, I have already sketched it for you earlier, is something like this, all right, proportional to z to the minus 1/4. Then what we are in effect saying is that if this is the value of h at z equal to L, this is h at z equal to L, then if I take 4 by 3 times this, if I at this point if I go up to 4 by 3 times this, so that this quantity is 4 by 3 into h at z equal to L. Then if I draw a horizontal line here, this will be the value of h bar for a plate of length L. H bar for a plate of length L is 4 by 3 times the value of h at z equal to L, that is at the bottom of the plate. That is what we are saying. So, these were two important results we were looking for which we have expressions. Given now a vertical plate with condensation taking place on it, I know how to calculate the local heat transfer coefficient and the average heat transfer coefficient. If I ask you, for instance, what is the average heat flux for a plate of length L, you can readily tell me now average heat flux for a length L will be equal to h bar, the average heat transfer coefficient, which is in watts per meter squared Kelvin, multiplied by the temperature difference T s minus T w. So, this would be the average heat flux for a plate of length L. So many watts per meter squared. Or if I were to ask you what is the average condensation flux for a plate of length L, average condensation flux for a plate of length L, you will say it is nothing but the average heat flux, that is h bar into T s minus T w, so many watts per meter squared, divided by the latent heat of vaporization. This would be the average condensation flux, and this would obviously come out in kilograms per second per square meter of the vertical plate. So, these are results which are consequences of getting expressions for the local and the average heat transfer coefficients. Now, some comments. This is the Nusselt formula which we have derived, the value expression for H and the expression for H bar. This is the famous Nusselt formula, as I said, derived in 1916 and still used extensively all over for calculations. Now, this result, some comments on the Nusselt formula. The first comment we will make is that the result which we have got, the result can be expressed in terms of what is called as a film Reynolds number, in terms of what is called as a film Reynolds number. There is liquid flowing in the film. Based on that flow, you can define a Reynolds number of the film called a film Reynolds number, and the result for H or H bar can be expressed in terms of that film Reynolds number. So, let me say what is the film Reynolds number first, and then give the result in terms of the film Reynolds number. The film Reynolds number is defined as the film Reynolds number, this is the condensate film, is defined by the expression equal to 4 m dot by b divided by mu. M dot by b is the flow rate of liquid in the condensate film at any cross section z, and v is of course the width of the plate. So, m dot by b is the flow rate per unit width. I divide it by the viscosity of the liquid, and the 4 is a number which has been by convention used, and we get therefore the what is called as the film Reynolds number. So, now if you use this definition, we know what is m dot by b for in our case. So, if you use this definition, you can show, it can be shown that for a vertical plate of length L, Using the results that we have derived, it can be shown that H bar, the average heat transfer coefficient, is related to the film Reynolds number by the expression H bar by K into bracket nu squared by G to the 1/3 is equal to 1.46 REL, the Reynolds number, film Reynolds number to the minus 1/3, where REL is the film Reynolds number at the bottom of the plate, where REL is the film Reynolds number at the bottom of the plate, at the bottom, that is at Z is equal to L. That is how REL is defined. So, this is an alternative result. This is an alternative expression for H bar, which is sometimes useful. The previous expression which we derived for H bar was in terms of the temperature difference T s minus T w. Now, the expression that we have got for H bar is in terms of the film Reynolds number. This is an alternative way of calculating H bar. Sometimes this is useful, sometimes the previous expression is useful. You should be able to derive this expression for H bar from the previous expression. I leave that to you as an exercise. It is a very simple algebraic manipulation, it should not take much time. So, please derive this expression which we have got from the previous expression. Derive the expression for H bar in terms of film Reynolds number from the previous expression for H bar which we have derived. So, this is the first comment we wanted to make on the Nusselt result. The next comment which we want to make on the Nusselt result is, when doing calculations with it, when doing calculations properties are taken of the liquid. You know, you need properties like K, mu, rho, etc. When doing calculations, properties of the liquid are to be evaluated at the mean film temperature. At the mean film temperature. And what is the mean film temperature? It will be T w plus T s divided by 2. So, when you are doing actual numerical work with this Nusselt formula, take properties of the liquid at the mean film temperature T w plus T s by 2, and this is a very good assumption, because the difference between T w and T s is usually not all that much. So, taking a mean film temperature works out very well. A third comment: the Nusselt formula for a vertical plate of length L, that is what we have derived, is also valid for a vertical tube of length L, so long as the diameter of the tube is large relative to the condensate film thickness. Keep this in mind. The Nusselt formula that we have derived for a vertical plate is also valid for a vertical tube, so long as the diameter of the tube is large relative to the condensate film thickness. And this is very easily seen. Suppose I take, just look at this now, I have this as a vertical plate here, all right. Here is a vertical plate. Now, look at this vertical plate, this is there. Now, if I were to fold this into a vertical tube, condensation will take place all the way on the outside of this tube, you understand. Now, so long as the film thickness, the condensate that is falling on the outside, the film thickness is small relative to the diameter, obviously, the result for a vertical plate is going to be valid for a vertical tube. A vertical tube is nothing but a vertical plate which has been folded into the shape of a circle. So, keep this in mind that the present result is also valid for a vertical tube, so long as the diameter is not small. And remember, the condensate film thicknesses are very small. We are talking of thicknesses which are usually less than a millimeter in thickness. Keep that in mind also. So, with these comments now, we have derived our formula for condensation on a vertical plate. Now, we will do a problem just to illustrate ideas. We are going to do the following problem. Please look at the text, take it down if you like. Saturated steam at 1.43 bar and 110 degrees centigrade condenses on a vertical tube 1.9 centimeters OD and 20 centimeters long. The tube surface is maintained at a temperature of 109 degrees centigrade. Calculate the average heat transfer coefficient H bar and the local heat transfer coefficient at the bottom edge of the plate. Calculate the average heat transfer coefficient H bar and the local heat transfer coefficient H at Z is equal to L, at the bottom edge of the plate means at Z is equal to L. That is the problem. It is a straightforward substitution into the Nusselt formula that we have just derived. No real complications. I just want to illustrate the whole procedure. So, let us draw the tube. Let us draw the tube. Let us say this is our tube. Let us say this is the tube, the vertical tube. Let us say this is the vertical tube and this is the wall of the tube. Condensation is taking place on the outside. I will draw the film thickness exaggerated again. So, I will say this is the condensation taking place on the outside with the film thickness of course exaggerated all round the tube. So, it is like condensation on a vertical plate. So, this is condensate film flowing down, this is the condensate, but mind you I am exaggerating this film thickness, keep that in mind, it is much smaller than this. So, this is the condensate film. Given T W is 109 T W, yes, T W is 109 degrees centigrade. Then T S is equal to 110 degrees centigrade, and we are told that the dimensions are 20 centimeters long. So, the tube is 20 centimeters long. The tube is 20 centimeters long. This is 20 centimeters. Now, we would like to calculate H bar and H at Z is equal to 20 centimeters. This is what we have to do. So, we have to take properties at the mean film temperature. Mean film temperature is equal to 110 plus 109 divided by 2, which is equal to 109.5 degrees centigrade. So, we need the properties of the liquid condensate at 109.5 degrees centigrade. Look them up in the tables for water. Properties of water at 109.5 degrees centigrade. If you look them up, you will get, look up the properties, you will get rho is equal to 951.4 kilograms per meter cube, K is equal to 0.685 watts per meter squared, watts per meter Kelvin, and mu is equal to 260.1 into 10 to the power of minus 6 kilograms per meter second. We will also need the value of lambda. So, from the steam tables, we can look up the value of lambda, the latent heat from steam tables. Lambda at 110 degrees centigrade and 1.43 bar. This is a saturated pressure corresponding to the temperature of 110. The value of lambda in the tables is 2230 into 10 to the power of 3 joules per kilogram. So, these are the properties. First, look up the properties. Now, substitute into the Nusselt formula. So, if you substitute into the Nusselt formula, you will get H bar is equal to lambda rho squared G K cubed upon T s minus T w into mu L, the whole thing to the 1/4 power to be multiplied by 0.943. That is our formula. So, let us do that. So, we get 943 multiplied by lambda, that is 2230 into 10 to the power of 3, rho squared 951.4 whole squared multiplied by G 9.81 multiplied by K cubed 0.685 cube divided by T s minus T w, that is 110 minus 109 multiplied by mu 260.1 into 10 to the minus 6 260.1 into 10 to the minus 6 and multiplied by the length of the plate, length of the tube, which is 0.2 meters. The whole thing to the power of 1/4. And if you work this out, you will get this is equal to 17,637 watts per meter squared Kelvin. So, you see what a high value you get. Note that high value, note the high value. I had started off my talk on condensation by saying that values in condensation and boiling are high. So, here is an example which shows that the values are always generally always in thousands. Now, this is our value of H bar. What is our value of H? That is very straightforward. H at Z equal to L, H at Z equal to L is nothing but 3/4 H bar. So, it is going to be 3/4 into 17,637. So, that is nothing but 13,227 watts per meter squared Kelvin. So, that is the second result we are looking for. First the value of H bar, then the value of H. Now, finally, if I ask you what is the thickness of the condensate film at the bottom edge, just to get a feel, what is the thickness of the condensate film at the bottom edge? That is very straightforward. Delta at Z equal to L is equal to K divided by H at Z equal to L, because we have an expression for the local heat transfer coefficient. So, all we are going to get in this case is 0.685, which is the value of K, divided by 13,227 so many meters, or if I want it in millimeters, it will come out to be 0.685 into 1000 divided by 13,227 millimeters, which is nothing but 0.052 millimeters. So, notice how small the film thicknesses are, and that is also worth noting in terms of numbers. We get high values of H, very thin films which are flowing smoothly down the vertical plate or the vertical tube, as is the case in this situation. So, we will next time now we will talk about condensation on some other geometries. We will talk on condensation on a horizontal tube and a bank of horizontal tubes, and put down some expressions for H bar for those geometries also.